So we have seen some basic set theory and logic, and we continue our discussion with functions. I think all of you have seen what are functions, but we will define it in a very precise mathematical way. So for this, for defining what a function is, we need the concept of a Cartesian product of two sets. So just for convenience, we will assume throughout the lecture that all sets are non-empty. Sets are non-empty unless specified. So just to make it easier, make the discussion easier, we will assume throughout that all sets are non-empty. So how do you define Cartesian product of two non-empty sets? So definition of the Cartesian product: the Cartesian product of two sets A and B, which is denoted by this A cross B like this, and it is the set of all ordered pairs A, B for A in A and B in B. So what do I mean by ordered pairs? Ordered pairs means that the first element must belong to A and the second element must belong to B. You cannot have the first element belonging to B and the second one belonging to A in this collection of elements. So if you write it in the set notation, so collection of ordered pairs A, B such that A in A and B in B. So this is how you define. So I'll use this notation to mean that this is how it is defined. Okay. So once you have the Cartesian product of two sets, you can define what is a rule of assignment. A subset R of this Cartesian product A cross B is called a rule of assignment if for any A in A, if any A in A, let's remove this for, if any A in A appears at most once as the first coordinate among the elements of this subset R. Okay, so it means that you cannot have A, B and A, B prime both in R is not allowed for B not equal to B prime. So if you have A in the first coordinate, you cannot have two different elements B and B prime in the second coordinate. So this is a rule of assignment, and the just some terminology associated with this. So the domain of this rule of assignment R is the set of A in A such that A, B is in this subset R for some B in B, and the range of this rule of assignment is the set of elements in B such that A, B is in R for at least one A in A. So we have the domain and the range, and now we can define what is a function. So a function is a rule of assignment, so it is can be viewed as a subset of the Cartesian product R together with a set B. So R here is a subset of this Cartesian product, again A cross B, and together with a set B naught which contains the image or the range. So sometimes the range is also called the image. Okay, so range of R. So let me mention here. So sometimes also this is also called the image of R. Okay, and so a function here is just can be written like this. So f with a colon, and you write A and then B naught. Okay, so we say that f is a function or a map from A to B naught. So this is the definition of a function in precise mathematical terms, in set theoretic terms, and with associated with functions are various properties that one can define. So one such is the injective function. So a function f from A to B, let's say, is called, so I'm just replacing B naught with B just to make it shorter, is called injective if for all A and A prime in A, the statement FA equals FA prime implies that A equals A prime. So this is the definition for an injective function. So you can think of it like this. So if A is a finite set like this and B is some bigger set, then an injective function takes one value for each of the points in the domain. It takes a unique value in the range. Okay, so you cannot have, for example, this second one, it cannot go to this one, so this is not allowed. Okay, similarly this cannot go here, or this cannot go here. Okay, so so this is what is meant by an injective function. Another type of function is a surjective function, and a surjective function is a function, let's say again from A to B, is surjective if given any B in B, there exists at least one A in A such that f of A equals B. So here I'm writing using this notation f of A to denote, remember that f was defined using a relation. So f of A here is the value, the unique value corresponding to the pair AB. Okay, so this is viewed in the relation R, and so whenever you have A in the first coordinate, there can be at most one value B in the second coordinate, and this value is written as f of A. So similarly here for the surjectivity, it just means that all elements of B are covered by elements of A, meaning that you have maps from all. So here you can have two different points of A mapping to the same one, but that doesn't matter. And here you have like this. So all elements of B have a corresponding element in A which maps to that element in B. So this is a surjective function, and we define a bijective function is a function which is both injective and surjective. So when you have both injectivity and surjectivity, as we call it, then this function is called bijective. Now let me give a couple of rules for constructing new functions from given functions. And so we have one way is to do the restriction of a given function f from A to B, and this is simply if you take A0 to be a subset of A non-empty subset, then the rule of assignment given by, so let me call it R naught. So this is the collection of pairs A comma B such that A is in A naught and this is in R. Okay, so you're just restricting all these elements of the relation A comma B, for which the first element belongs to this subset A naught, and usually it is denoted the restricted function. So there is a function associated to this rule of assignment now. So the restriction function is denoted as f with a vertical bar, and you write A naught in the bottom, and this is a map from A naught to B. So this is a restriction of a function. So in pictures, if you have, say, this is A and this is B, and you have some points in A, some points in B, and you have some map, let's say like this. So it need not be surjective. So one point here is left out, but it doesn't matter for the definition of the restriction. So suppose that I take A naught to be this subset of A, and then the rule of assignment just takes a point here and associates the points in B. So let me write this in red. Takes this point in A naught these points and associates the corresponding points in B. And this is now yet another rule of assignment and gives you a new function which is called the restriction. Another way to define a new function is when you have two given functions. So let f from a to b be a function and g from b to c be a function. So note that the range of f is the domain of g, and now define a new function which is denoted as g circle f, and it is called the composition of g and f, and this is given by this formula, the g composed with f. So this is for a in this domain of f. So if you take any point a in a, then f of a now lies in b, and so now you can apply g to this function. So first apply f to a and then apply g to the result. And so now g composed with f is a map from a to c, because first you map from a to b. So let me draw a picture. So here a, b and c are three sets. So the first one gives you f, this is f, and the second one gives you g. This is g, and so g composed with f, if you take g composed with f, then this point first maps to this point and then to this point. So here there is an arrow, okay, like this, and similarly this point first gets mapped to this point, and then it again goes to this point. So there is again an arrow here, and the last one gets mapped first to this point and then to this point. So there is an arrow here. So this is g composed with f. So in terms of arrows, it's easy to see, but of course you cannot draw pictures all the time. So this is the formal definition in terms of the functions g and f, but you can also write the rule of assignment for the composition. The rule of assignment for the composition is the collection a comma c. This is an element of a cross c, the Cartesian product, such that there exists a b in b for which ab belongs to the rule of assignment for f, which I denoted by rf. So this is the rule of assignment for f, and bc is in rg. This is the rule of assignment for g. Okay, so this is the rule of assignment corresponding to the composition g composed with f. So in this way we can construct new functions in these two ways. There are also other ways to do that, and we will see them later. Now once you have functions, there is a very nice construction called the indexed collection and indexed or arbitrary unions of and intersections of indexed collections. So this is in terms of functions. Okay, so suppose that A is a non-empty collection of sets, and J be another set. Okay, then A is called an indexed collection over J. Okay, if there is a surjective function f from J to this collection A. Okay, so the surjective function means that for any set A belonging to this collection capital A, there is an alpha. There is an alpha in J, so it's an element of J, such that f of alpha is equal to A. So we write A subscript alpha as f of alpha, just to denote that the set A is corresponds to the element alpha in J. So this is an index collection, and this we will use this many times in this course, so it's something to keep in mind. And arbitrary unions and intersections over this collection J of these sets A alpha, this is by definition the set of all elements X, such that X belongs to A alpha for at least one alpha in J, and the arbitrary intersection is defined to be the set of all X, such that X belongs to A alpha for every alpha in J. So note that here I am assuming that if J is non-empty. Now if J is empty, if J is the empty set, then by convention we set the arbitrary union over this indexing set J of these A alphas to be empty, and we do not define, not even by convention, the arbitrary intersection when J is empty. So in this way we have a nice way to describe a collection of sets using an indexing set. So if A is just the finite collection, so suppose that as an example you can take A to be the set A comma B, just two sets, then you can take J to be the set 1, 2, and then the arbitrary union of this set of these sets is the same as the this union I in J AI. Note that your function here from J to this collection A can be defined as f1 equals A and f2 equals B. This is what indexing means. So this 1 goes to A and 2 goes to B. So here this is A1 and this is A2 now. So you can rewrite this as this indexed union, and this is nothing but A union B. Okay, so similarly you can have more than two sets, and then you will have a finite union. And similarly, you can also have finite union and finite intersection as well. But of course, we will use these indexing sets in full generality, and they will be arbitrary in general. So we stop our description of functions now, and we will go on to talk about finite and infinite sets in the next lecture.